Good morning. Oh, it's noon already. This is the solution to the quiz 7 on steady heat transfer. So the question is, consider steady two-dimensional heat transfer in a long solid bar whose cross-section is given in the figure below. The measured temperatures at selected points on the outer surfaces are as shown. The thermal conductivity of the body is K is equal to 20 watts per meter degree centigrade, and there is no heat generation. Using the finite difference method with a mesh size of delta x is equal to delta y is equal to 1.06 centimeter. Determine the temperatures at the indicated points in the medium. Hint: take advantage of symmetry. So, um, looking at this, we can obviously see that this node 3 here is the same thing as node 2 here, because what is happening at this right hand side is also the same thing as what is happening at the left hand side. Node 4 also is the same thing as node 1. So we can turn this figure into this. So we have, that is, you bring this right hand side to the left hand side. So when you join it together, you have something like this, like a trapezium. So this is our node 3 now. This node 3 has moved from here to here, while node 2 has moved to the right hand side. Then 4 is here now, and 1 is here. So whatever temperature you have for 2, the same thing you're going to have for 3. Okay, so we have the general heat equation, that is partial square T over partial S square plus partial square T over partial Y square plus G dot over K. That's for two-dimensional is equal to 0, since it is steady. So, but in this case, we don't have energy generation, so this part is equal to 0. So we are left with partial square T over partial S square plus partial square T over partial Y square is equal to 0. So we have to discretize this partial differential, because there's no way we can solve this. So how do we discretize this? We have, for this part alone, you have Tm plus 1, that is, you move to the right hand side, minus 2Tmn, that is the particular node, plus Tm minus 1, that is to the left hand side, all divided by delta S square. Y for the y, partial square T over partial S square, or partial Y square, we have Tm comma n plus 1 minus 2Tm comma n plus Tm comma n minus 1 equal to 0. So all divided by delta Y square. So, but from the question, we're told that our delta Y is equal to delta X. So we can factorize and say 1 over delta S square is equal to Tm plus 1 comma n minus 2Tm comma n. That's for this. Then minus 2Tm comma n plus Tm minus 1 comma n plus Tm comma n plus 1, then plus Tm comma n minus 1, all equal to 0. So from the equation we had earlier, from there we can factorize. We have Tm plus 1 comma n plus Tm minus 1 comma n minus 4Tm comma n plus Tm comma n plus 1 plus Tm comma n minus 1. So if you divide both sides, multiply both sides by delta S square, so you are left with Tm plus 1 comma n plus Tm minus 1 comma n plus Tm comma n plus 1 plus Tm comma n minus 1, then minus 4Tm comma n equal to 0. So this is the finite difference equation that we'll be using for the internal nodes. So since all the temperature we want to find, they are internal nodes, so this one applies. We can use this equation to solve for the temperature. So we'll look at how we're going to derive each of the nodal temperatures now. So to derive the equations of each node, so for node 1, like we've derived earlier, we said for us to get the equation for the temperature at node 1, you move to the left. So to determine to the right. To the right, we have T2. And then to the left, we have T3. But remember, our 2 is also the same thing as 3. So we can replace that T3 as T2. So if you move to the top, you have 100, which is this. If you move down, you have 200 minus 40 ml, which is the node 1 itself, is equal to 0. So if you add this together, you have T2, 2T2 plus 300 minus 41 is equal to 0. So that gives us equation 1. Then for node 2 now, we have to the right, we have 100. To the left, we have T1. To the top, we have 100. And to the bottom, we have 200. Then minus 42 is equal to 0. So if you add these together, you're going to get 400 plus T1 minus 42 is equal to 0. So we can rearrange this equation as 4T1, as this. If you go to the other side, minus 2T2 is equal to 300. And then minus, at least if you go to the other side, minus T1, then plus 4T2 is equal to 400. So this equation 3 and 4 is what we can solve with simultaneous equation. And if you use your calculator to solve this equation, you are going to have your T1, which is the same thing as T4. T1 and T4 are the same, so you are going to get 142.8 degrees centigrade. And then T2 and T3, which is the same, you are going to have 135.7 degrees centigrade. Thank you. God bless.